So I actually did a test, and what distance does the Umbra and Penumbra start to happen using our sun? Well, the answer is hey everybody, Christmas will thrive and survive. This video is going to look at the science, and we're going to do science, actual real observations here to see if what NASA and mainstream scientists has been trying to sell us, and which has been universally accepted without question, is the Umbra Penumbra that is created by the sun, moon, and earth, whatever, depending on the type of eclipse you're looking at. And what we're going to be looking at here is this comes from my Jupiter video. I'll have a link below to that, and maybe I'll put a card in the upper right hand corner here. The idea that we have a 70-mile wide shadow caused by the moon supposedly blocking sunlight on the earth. Okay, I had to cut in here just to show the ridiculousness of the comparison between the two and how off the shadow really is on Jupiter. Let's look at this. This is are we seeing the whole half of the Earth? Who knows? Same thing with Jupiter, right? So let's look at this, and let's look at Lake Okeechobee over here. Lake Okeechobee in Florida is just under 30 miles, 39.85 miles wide. So it's, you double that, you get 80 miles. So you double this, that would be the shadow that the solar eclipse made across North America as it was going across. So let's take a look at that just real quickly. And we're going to compare that to Jupiter. So here it is, Lake Okeechobee. Sorry, it's not very clear here. But again, this is roughly 40 miles. It's almost a circular. It's a little bit more north-south than east-west, but we're going to go with 40 miles. And what I did was I did the math. If you multiply the width of this by 2.3, then you get 70 miles wide. So there's Lake Okeechobee. Forget about this outer circle. I was just using that for a different scale. We're going to use something better than that. And so what does that look like if we put that on the map? So at Lake Okeechobee, where this black spot is right here, the width of Florida is almost exactly 140 miles. It's like 139 point something. So I did that on Google Earth. Let me check that. Let's take a look at that. Here we go. You see this yellow line going across right here? I measured that. That's cutting straight across Lake Okeechobee in Florida. That's 139.33 miles. So that's 70 times 2 is 140. So we're not going to get much better than that as far as scale. So if we take half of this diameter across and make a ball out of it, we're going to end up with a 70-mile wide shadow. Hopefully everybody can agree on that. That's just simple. So that's what I did here. I took halfway across, and I know this is, when it's on this kind of scale, it's not very circular. It's just, you're seeing the imperfections in the graphics. And but anyway, that is a 70-mile wide shadow that we would see on the Earth. So what does that look like if we zoom out, okay, and look at the whole disk? Let's take a look at that. All right, now I'm going to be able to show you the whole disk here. Here it is again. It's actually a little bit bigger than halfway across. So again, I'm going with the other side a little bit here. We're going to select this, and we're going to copy it and move it to around the middle of the country where it went through. So if we had a satellite picture like we had with Jupiter, what would that look like? There we go. Look at that. Little teeny little dot. Little teeny Rosanna Dana. Look at that. Now, let's compare that to Jupiter. Yeah, there's a little bit difference, huh? And if we have to, well, let's do this. Let's look at the difference here. Now, you're going to say, "Oh, you're not showing all the Jupiter." Well, go look at my other video. and go to the Jet Propulsion Laboratory site that I left a link to where you can see the entire disk. But let's compare Jupiter's size to the Earth. Here we go. Look at all these Earths that can fit into the side of Jupiter. All right. So how big would the speck be? All right. There is no comparison. Only cognitive dissonance would allow you to destroy your own thinking here and say, oh, they're pretty much comparable, Rich. There's a little bit different angles and the Umbra. Oh, yeah, Umbra Penumbra. Let's get into that because this is the heart of the meat of the matter right here. Okay, back to the video that was sent to me. Now, granted, this is going to sound a little weird pulling in the Kennedy assassination here. But just think of the narrative that was given that people believed simply because they would not trust what their senses and logic told them. Now, I'm not going to show it, but almost everybody probably listening to this video, watching this video, has seen the assassination of Kennedy, where he was shot and his head went back and to the left and the front right part of his head was blown off. And yet, because the government said that it was a lone assassin in the back, this guy right here, Lee Harvey Oswald, just because the government said that, most of the people believed it, and the CIA came up with the term conspiracy theory to degrade anyone who actually wanted to use their logic. You see, logic tells you that if your head goes back and to the left, that means you were shot in the front right. So there are some people that actually use their logic and were able to tell before the 2018 release of the CIA files that show that, yes, indeed, there was an assassin in the front. And you can look that up. That was released by Trump, I believe, about a year ago. So, or 2 years ago. And there's still more to be released there also. What can our logic tell us about the Umbra Penumbra? Are we making an assumption that just like the Kennedy assassination, that what the government tells us, and NASA is most definitely an offshoot of the government, just because what NASA tells us it's true, even though do our senses tell us this? Do we just accept everything blindly, like 90% at least of the people did with Kennedy's assassination? Well, let's take a look at it real quick. All right, now I have to use a disclaimer. Do not use a local light that's inside the house or inside your garage or something like that. If I did that, I would be absolutely hammered without end. We don't need to use an artificial light. All we have to do is use the real sun. Here's the argument. It's always because the sun is larger. Because the sun is larger than the object that is blocking the sun, we get this Umbra Penumbra effect. And particularly the effect we get with the the solar eclipses. And we have the shadow, as you can see here, it comes down to a point, and then it goes the other way. Totally ridiculous, but we're not going to get into that. I've gotten to that in other videos. Because what's ridiculous about it is at 93 million miles, the rays are virtually parallel and they do not spread out in space without an atmosphere. So that's not the argument here, though. But all you have to have is a larger sun and a smaller moon or a smaller blocking object. That is the whole thing. If you look up light physics, so to speak, with the sun and with the eclipses, they will always say, oh, if it's a larger object, like the sun, it's going to produce the Umbra Penumbra just like we supposedly have with eclipses. Let's look at something local using the same sun that is used in eclipses. Now this is simply a telephone pole that I shot earlier today. And in the next video you're going to see how the shadow does. This was late in the afternoon. And you'll see how it does when it is very long in length, and this is the actual physics that we can actually prove ourselves in person. So let's take a look at it from a purely scientific and observational point of view. What do we have here? No matter what object we use on Earth, it's going to be smaller than the sun. So we've got a larger sun. Blocking any object that blocks it is going to be smaller. So we don't have to worry about having an object that's larger than the sun. And let's just say we had a blocking object that was located here. So here we have an object. And what if we were somewhere in here? What kind of shadow size should we see according to this diagram? Well, we should have something like that, right? Sounds logical. Because the argument is the farther you're up in the cone, the larger the shadow that would be produced. That's why supposedly we have a 10,000 mile and greater shadow on Jupiter, because it's a little bit farther up the cone. So what if we were further down here, let's say in here, what size shadow should we have there? Yeah, something like that, right? So the closer we get to this focal point, the smaller the shadow would be. And then, of course, when we come out on the other side, the further we get away from it, the larger the shadow should be also. Logical, right? Makes sense. So if we have an object that is blocking sunlight, it should have the properties of that should go down to almost nothing, and then we should see that shadow come back out larger again on the other side. The properties of that should go down to almost nothing, and then we should see that shadow come back out larger again on the other side. That's just the way it is, folks. That's what they're showing you. And that's the argument that they have for the Umbra Penumbra. So let's take a look at some real life situations. Now, as we cycle through these pictures, I want you to notice that we have things that are very close to the surface. We have clouds that are very high in the sky. We have clouds that are low in the sky. We have buildings. We have all kinds of different things that are creating shadows. And again, as we cycle through these, I want you to tell me where we have an Umbra Penumbra on any one of these. Do you see it? I mean, some of these at some height should have the shadow get smaller and then come back larger again. And we're going to look at the example I have of the light pole, and that is going to tell us exactly how light and shadow works with the sun when you have a larger sun that is blocking a smaller object. So you can go ahead and pause through these pictures if you want, but you're never going to see an Umbra and Penumbra. What you will see in some cases, like here, you see what I call shadow degradation, and we're going to talk about that. And that is exactly what we get. We do not get an Umbra Penumbra. So let's now go back to the light pole that I showed earlier, and you can do this yourself and see exactly how it works. Now I'm going to manually advance through this video. Here I am standing. I'm 6'3". You can see how low in the sky the sun was to produce a shadow this long. And here is the light pole that I showed earlier in this video. And what we're going to see is, as we get way out there, we're going to see how shadow degradation works. And I'll show you an example more close up how that works also. And this is something you need to go out and do yourself, and you can actually measure this out and see. First of all, measure the pole. And I'm just going to say the pole was 8 inches in diameter. I don't know what it really is, but we're just going to use that as an example. What you will find is the shadow will never be greater than 8 inches. Never. Now, what you will also notice is, and this is more, you can notice it with a ball or something like that. I'm going to show you a ball that I did in another video. The shadow, when it is very close to the object, has no degradation whatsoever. However, once it gets beyond 1 diameter greater distance than the object itself, you start to get a little bit of degradation. It does not happen when you're closer than that. For example, if this is 8 inches in diameter, the first 8 inches of this shadow will not have any degradation whatsoever. It'll be a nice, crisp, sharp shadow. No umbra, no penumbra. Then as you get farther and further, 2 diameters away, 3 diameters away, and on and so forth, you get more and more degradation as you go out. At about one diameter away, you get about a 1% degradation, roughly. So 1% of 8 inches would start to be degraded on the outside of the shadow. Now, as you walk this through, you will see that the size of the pole gets more and more narrow, apparently. It's the same diameter all the way up. But what happens is the shadow degrades to where there is no more shadow. The light starts filtering through. It's the only way I know how to say it. To where it just whittles this away to nothing. And it never then comes back with an Umbra Penumbra where you have another, where it comes back and gets larger again. And remember, this is the same sun that is used for solar eclipses, so it should work on any scale. It should not be different just because we're talking about a smaller object. In fact, we should be able to see it easier because we don't have to have the great distances to make the ratio and proportion correct. So what you will notice is, let me see if I can show this here. Right about there. Let's see how much I can show here. It degrades so badly when you get out so far that it just starts losing, you start losing what the object actually was. More and more light bleeds through. You do not end up with an Umbra Penumbra. You have no sharp edge whatsoever after a certain distance. So according to the diagram, this should get smaller and then get larger again once we reach that focal point. It doesn't happen, folks. So let's take a look at a ball that I did in an earlier video and compare that. So I actually did a test, and what distance does the Umbra and Penumbra start to happen using our sun? Well, the answer is never. You never get an Umbra Penumbra. Let me explain what I have here, and then we'll be done. What I did was I took different balls of different sizes, and I cast shadows from our sun onto different objects. I even did smaller balls onto larger balls onto smaller balls, all kind of different distances. And I also did a video where I took coins, and started going more and more diameter distances away to show how light degradation works. And if I was to zoom in on this, I'm not sure if it'll show here. Let's see what we can do here. You can see that there's a little bit of blurriness around the edge of the ball here. Why is that? It's because the shadow is approaching or has just exceeded one diameter in length away. Let's just say this ball is 12 inches in diameter and the shadow is just over 12 inches, 13 or 14 inches away from the ball itself. That's when you start to get degradation around the edge. The further away you put that ball, the more diameters away, the more degradation you get on the outside. You never, ever end up with an Umbra Penumbra. I challenge you, you can use the exact ratio and proportion as I did. I used a ball that was about the size of the moon, a ball about the size of the earth, ratio and proportion wise. I did the distances correct. I cast the shadow. I could not produce an Umbra Penumbra using our sun, which is larger than the objects I used. Correct? So just like with the Kennedy assassination, you can use your common sense and your eyes to see that the Umbra Penumbra cannot be proved, ever. And during the Great American Eclipse, there was never a partial shadow. And people want to argue, well, the partial eclipse is a shadow. No, if I take a light bulb and I cover it partially, it doesn't mean I created a shadow. It just means I diminished the light some. Remember, by their science, the shadow should get smaller and smaller as you go away from it, correct? As you make the blackened object further away. Do this. Tell me if it happens. It doesn't happen, folks. all you get is the same size with light degradation around the outside. That's what you end up with. And you never end up with a shadow that gets smaller to a point and then comes back on the other side. I don't care what distances you use. So the reality is we can demonstrate in physics that there is no umbra penumbra. So if you're going to bring an argument up like the video I was sent, and again, I am very appreciative of the video, you're making an assumption right off the bat that the umbra penumbra is true. And I have gone out with measurements, with all kind of things, and proven that it is not true, using our sun as the source. God bless everyone. Take care.